Hello, my name is Thijs Heus. I'm an assistant professor of physics at Cleveland State University, and in the next half hour or so, I'm going to talk about the scientific basis of climate change. What is going on in the climate system? How does it work in the first place? And what are the projections? How is it going to change over the next several decades? And what can we do about it? So, first, a little bit about me. I'm, as I said, an assistant professor of physics at Cleveland State University. I've been there since 2014. Before that, I did my PhD in Delft in the Netherlands, where I was born and raised. And then I did some postdoctoral research at the Netherlands Meteorological Institute. And then for 5 years at the Max Planck Institute for Meteorology in Hamburg in Germany. And then at the University of Cologne for another year. Especially all of these institutes are leading in developing understanding of the climate system, but especially the Max Planck Institute is one of those institutes that is running one of the leading climate models in the world. So that's one of those places where I really got a good idea of where the weaknesses of climate models are, where the strong points are, what the goal is of what the direction is of the research for the next several years. My own personal interests in the climate system are in clouds and in atmospheric boundary layers, so the layer of roughly a kilometer, a mile above us, where all direct interactions with the surface happen, where that has a direct impact on us. As it so happens, those clouds, and especially those boundary layer clouds, also have a very immediate impact on climate and are one of the largest uncertainties in climate. If you want to know more about what I'm doing, if you're interested in that kind of stuff, there's a YouTube link over here that gets you to CSU directed video about my work. Okay, so let's talk about what we're going to discuss today. So first of all, the most important part of this talk is going to be on how does the climate system actually work? Why does Earth have the temperature roughly that it does have? And of course, we're starting with the sun, and then pretty much immediately we're going to look at greenhouse gases, including CO2 and other greenhouse gases. Then of course, the climate system is not as simple as just sun plus greenhouse gases. So on top of that, we need to take into effect feedback cycles, what we call climate feedbacks, interactions with other things in the climate system. Once we have a good understanding of how climate feedbacks and the climate system as a whole kind of sort of works, we're going to look at how good climate models are doing, what are the predicted outcomes over the next 100 years. But we're also going to have a look at some more current and local topics, such as, for instance, hurricanes and forest fires. Now finally, and at least if time allows, we're going to have a bit of a talk of mitigating and adaptation. What can we do? What do we need to do to make sure that the world is still a livable place in 2100 for, let's say, my children will hopefully still be alive to see that. Maybe I will still be alive. Probably not. Okay, so let's start with the climate system, or at least climate change. Of course, one of the first arguments you would ever get into if you have the unfortunate business of getting into these kind of arguments would be, but the climate has always been changing. Yes, it has. There are very many ways why the climate could be changing. The most obvious one would be, well, if the strength of the source of all of our energy, of all of our heat changes, that is the sun, then obviously our climate will change as well. Volcanic eruptions may be a big factor. All kinds of other mechanisms On smaller timescales, we have El Niña, La Niñas. On very small timescales, we have simply weather. There are all kinds of contributions that can change that can change the atmosphere on Earth, that can change the ocean, that can change the land as we know it. But for the very first time in global history, there is a new factor, and that new factor would be us. For the very first time, there is one particular species that has the power to change the climate that we're living in. Now, that could be seen as something horrible, of course, but we could also just as easily argue that, let's be optimistic about this, if we have the power to change this to a state that is clearly undesirable, and even though that's more or less a personal or political opinion, I hope that many of you would agree that the trend that we're in is fairly undesirable. But if we have the power to change it into an undesirable state, we probably also have the power to bend it backward and to go to a state that is actually decent to live in, like more or less our current climate. So we'll go through that kind of stuff later on in this presentation. Okay, let's first have a look at where our source of energy is coming from, and that is of course the sun. If we start out with the sun radiates energy in every possible direction. It's a black body radiator, and that is something that since the days of Max Planck and maybe even before, we could fairly well calculate what that energy should be based on the time. So for the past 100 plus years, we kind of know, based on the temperature of the sun, chemical reactions, nuclear reactions at the surface of the sun, the temperature of the sun is a certain amount. Therefore, the amount of energy that passes along the Earth, that's being captured by the Earth, has to be a certain amount. Turns out that amount of energy is something like 1300 watts per meter squared. But we're dividing it over the entire globe. Half of the globe is night, half of the globe is day. At some point, we're at the North Pole or at the South Pole. Not a lot of light is shining there. So if you average all of that out, you end up on average with 340 watts per meter squared coming in. Those 340 watts per meter squared over there are coming in. But of course, if you look at any kind of picture of the Earth, there's a lot of white there. What does white do? It just reflects light. So 26% is immediately reflected and 4% more on Earth. So roughly 30% in total is immediately reflected because they're clouds, because they're ice, glaciers, polar caps, or because they're deserts. Any desert is also fairly bright and fairly pronounced on any kind of satellite picture of the Earth. So we're then left with 75% or so, of which 23% goes to the atmosphere, is there to just warm up the atmosphere. And the rest, roughly half of it, finally reaches the surface of the Earth. Of course, 2/3 of the Earth's surface is ocean, so 2/3 of that, 1/3 of the total original budget goes into the ocean. The rest goes to the land. Okay. From that point on, we could calculate it at that point what the temperature would be of the Earth. Or we could say, yeah, some of that energy, the Earth is warming up to a certain temperature and it's radiating heat out, just like you would do, right? You feel warm. Or if you look at an infrared camera, and you look at your own home, you see certain spots that are not as well insulated and the warm air is coming out, and those are the red spots. you radiate heat out. So that heat is radiated out from the surface, going up, and some of it goes all the way up to outer space, but some of it is captured by the atmosphere and sent back. Well, and then half of it is being sent back, half of it is being passed on to outside. So that's basically what clouds are really good at. That's one of the things that clouds are very good at. But this, in effect, is the greenhouse effect. So it's not just clouds, it's water vapor. Water vapor is probably the most important greenhouse gas that we have on Earth. It's also CO2, methane, a couple of other gases that are really working like a blanket that keeps the Earth warm. Finally, we have a little bit of air going up. That's what we call convection. A mixing of air, and there's some energy involved in that. So, if we take everything into account, and we would remove the entire blanket of CO2, of water vapor, of all the methane, of all the greenhouse gases that we have, then we can do a couple of calculations. 1. What if all the energy that the sun radiates to us is being absorbed? So the albedo, the reflection of sunlight, is 0. Then we end up with a temperature of roughly 50 degrees Fahrenheit, which is, not too far from what it actually is. But if you take all that reflection into account, all these polar caps and all this, all the clouds and all that, then we end up with roughly minus 10 Fahrenheit, which is pretty much the same temperature as the moon. And now and clearly not the temperature that you want to live in. Now if we include the fact that the atmosphere is a greenhouse, that it has all this CO2 and especially water vapor and methane in it, all these gases together work as a blanket and lift the temperature back up from minus 10 Fahrenheit to roughly 58 Fahrenheit, the average temperature of the Earth. Averaged over the equator, the poles, days, nights, etc., etc. So the greenhouse gas is really important because it lifts the temperature of the Earth by roughly 70 degrees Fahrenheit. Now you immediately can see the problem here, because we're not talking about introducing a brand new greenhouse effect that has to be doing something monumental and enormous. We're only asking the greenhouse, what we're doing here, if the temperature on Earth is increasing by, let's say, 5 degrees Fahrenheit, 6 degrees Fahrenheit, then that's effectively the same as just the greenhouse effect enhancing by only 10%. So significant, but not that earth-shocking, right? If you get a 10% raise of income, that's very, very nice, but you're not suddenly gonna be able to quit your day job or anything like that. So 10% is all it takes to raise the temperature from very livable and nice as it's been pre-industrial to something very hot with everything that we can see is happening now. Okay, so as I said, without a greenhouse gas, we would be pretty much like the moon. With the greenhouse gas, CO2, methane, water vapor, we would end up, a lot warmer, like we are here. And if you pull that all the way to the other side, with an abundance of especially methane, we'd end up with Venus. Venus is quite a bit closer to the sun than we are, but not that much closer. Meanwhile, the temperature of Venus is roughly 800 Fahrenheit. And that's all due to a massive runaway greenhouse effect. Apparently there's a lot of methane in the atmosphere of Venus, and of course also a little bit of phosphine, as was recently discovered and maybe a hint that there might be actually some kind of microbe or some kind of unknown chemical reaction happening in the clouds of Venus. What do we mean with could a runaway greenhouse effect happen on Earth? In theory, at least, yes. A runaway greenhouse effect would, for instance, include a little bit of extra CO2, which would melt the polar caps, melt the glaciers. So there's less white on the top of the Earth. So we would have less albedo, less reflection of sunlight. Therefore, more sunlight being absorbed. If there's more sunlight being absorbed, temperature gets higher, it gets warmer, so more glaciers would melt. So it gets warmer, so more glaciers would melt, so it would get warmer, etc., etc. So that would be a runaway effect. The other way around is also possible, of course. If for some whatever reason we end up with some kind of ice age, you'd get a much higher albedo, much more reflection, you'd get more ice, etc., etc., until the entire globe, in theory, would be covered by ice. This has happened here and there in the solar system, at least. We call that the snowball Earth. Other effects could be, or at least feedback effects, are all working this way. So if you have a warmer temperature, you would evaporate more water from the ocean into the atmosphere. Water vapor is a strong greenhouse gas. So if you increase the temperature, you get more water vapor in the atmosphere. More water vapor is more greenhouse effect. Gets warmer, so you would get more evaporation. More water in the atmosphere. Warmer, more evaporation, etc., etc., etc. That's why just looking at CO2 is not quite enough. However, we've been looking at CO2 for quite a while. Look at this quote. The furnaces of the world are now burning at 2 billion tons of coal each year. When this is burned, uniting with oxygen, it adds about 7 billion tons of carbon dioxide to the atmosphere yearly. This tends to make the air a more effective blanket for the Earth and to raise its temperature. The effect may be considerable in a few centuries. This was a nice piece, nice quote from not a very obscure place and not so very recent. It was actually Popular Mechanics, the nice venerable Popular Mechanics, in March of 1912. They were spot on back then. So this was not something obscure that only scientists knew about in, let's say, the 70s and the 80s. This was something that scientists knew about in the 1870s and 1880s, and that the general public was at least informed about in the early part of the 20th century. This was something that Congress hearings were done about, and Congress study groups were formed about, that were essentially spot on back in the 1950s, 1960s, or in 1960s under President Johnson specifically. So, if we look, one fantastic thing that happened to have happened for this kind of research was that we have a atmospheric CO2 measurement in Hawaii, and for sure we see that the amount of CO2 in the atmosphere is incredibly small, only 300 something parts per million. But it has steadily been going up, and this is in Hawaii, this is very remote, there's no immediate source of, hey, there's a factory next to it, and suddenly the CO2 concentration goes up or anything like that. But the CO2 concentration has steadily gone up from around 300 to about around 400 and now above. So in that sense, immediately that's a third extra CO2 in the atmosphere. This amount of CO2 translates roughly to 4 degrees Fahrenheit right there. That's on average. Now, this also means that not all of that CO2, since it takes a little while for all that CO2 to build up into the atmosphere, not all the CO2 that we've exhausted has already been incorporated in the temperature. That will take a little while. If we zoom out just a little bit, instead of looking at the past 50 years, we're looking at the past million years or so, or almost. We see that the CO2 concentration is essentially at its highest point since, well, all of that period, since all of the ice ages. So if we stop emitting now, and this is a key point that is really easy to forget. The CO2 emissions are kind of the feathers in your blanket. Each time you emit some CO2, you're adding another feather to the blanket. So if we stop emitting now, if we get back to zero emission pre-industrial, that does not mean that the temperature would go back to pre-industrial right away, because we still have that blanket. If we want to get to the temperature that it used to be, this temperature even from the 50s or the 60s, 4 degrees Fahrenheit lower than now, then we need to take away the blanket. So if we want to get back, we need to get to negative CO2 emissions at some point, at least. Okay, so if we look at the global temperature change, and this is from the IPCC report of 2014. So if we look at the CO2 emissions, would account for roughly 1.5 degrees Fahrenheit of temperature change. On top of that, methane, especially industry, but also cows, add another degrees. Then some of the other greenhouse gases add some more and more and more. But then there are other impacts, like aerosol. Any kind of dust would create a reflection of sunlight. So that is then going down by, let's say, 0.5 degree. But those very small dust particles are very good in creating cloud water droplets, can form on top of them. And if you have very small droplets, they'll stay for a long time, as opposed to if you have no aerosol, no dust in the atmosphere at all. You get very big drops and they'll rain out immediately and you end up with pretty much no clouds. So there are those kind of effects that in principle decrease the amount of, thanks to the human interventions, the temperature actually has gone down a bit. Also, thanks to human interventions like deforestation, we increase the, more desert, therefore we increase the albedo, and therefore temperature decreases just a little bit more. Finally, there's a little bit of effect of the sun. But if you look at this one, I hope you agree with me that between the amount of effect from the CO2 or from methane or from anything else, relatively speaking, the amount that you get from the sun is very, very small. Therefore, solar fluctuations don't add that much to climate change. Not on the scale that we're talking about, not on the scale of 10, 20, 50, 100 years. So if you add all of that up, then we end up with roughly 2 degrees of global temperature change. With a significant error margin. That's what the error bar on the right says. Where does that error bar come from? Well, not so much from CO2, because that effect has a very small error margin, or relatively small error margin. We kind of understand that. The biggest uncertainties are associated with the aerosols. How much aerosol we have in the atmosphere and how much clouds respond to those aerosols. That's not quite clear. That's where a lot of research sits. And that's what adds to this significant error bar. However, no matter what, we know that the temperature of the atmosphere has increased a lot and will increase a lot given our current CO2 exhaust. Okay, so now let's have a look at climate models. How good are climate models? How confident are we in climate models? Anyway, so if we look at climate models over the past, what the climate models have been doing, then you see that there are all kinds of climate models, and you can have a look at what they've been doing previously, before basically today, or they were run in this case in 2005. And you see, and the black lines are the different observations made by satellites, made by surface level instruments, etc., etc. And you see that all in all, the observations and the climate models agree with each other reasonably well. This is still true if we look at what happened since 2005. So in 2005, those particular climate models made a prediction what the temperature would be in 2015 or now in 2020. Turns out that whatever the climate models predicted is still pretty much true. If you look at, okay, that's unfair, one might say, because there's this enormous spread in climate models here. But if you look at what is the biggest difference between the red lines and the blue lines here, well, that's just the amount of CO2 that we're exhausting. That is basically what is setting. The biggest uncertainty in climate models is not how the climate system works. The biggest uncertainty in climate models is what we are doing. How much CO2 and how much other greenhouse gases we're adding to the climate system. This is even true if you look at the oldest climate models from the 70s or from the 80s. They were very crude. They couldn't do fancy things like model all the clouds or model all the aerosols or the ocean currents or anything like that. But even there, they had the general trend correct as long as you would feed them the actual pattern of pollution that we have ended up doing there. So the biggest uncertainty in climate models is the amount of CO2 that we are emitting. Other than that, the climate models are doing pretty well. Now, if we then look at, different types of emission scenarios, which gets very technical if we're zooming into the IPCC models, then we can say, if we're just going to do business as usual, full on, same exponential growth as we're looking at, then we're looking at roughly 5 degrees Celsius, so 5.5 degrees Celsius, so let's say 10 degrees Fahrenheit warmer in 2100 than it was in 1900. If we're doing a really good job, then maybe it's somewhere between 1 and 2 Celsius. Those two scenarios are getting less and less likely, so we're probably looking at somewhere in the order of 2.8, 3.3, something like that type of scenario, based on the amount of CO2 we're emitting. But that's on average still. If we now look at the, of course, there's a lot of variability from place to place. So let's have a look at that. Let's have a look at the temperature in 1979 compared to the temperature in 2010 and how that evolved. And we can see that the average temperature, average has to be 0. So we start out with a relatively low temperature because we know that the temperature is going to increase. And we see that the temperature will start to go higher up. There's some fluctuations. Some years there are are warmer than others. Some years you'll see over here off the coast of Peru a little bit of very warm water. That's what we call El Nino, and that means that there are all kinds of those are the years that are. Oh, there was a strong one you saw, and that was a strong El Nino in 1997. And sometimes there's a La Nina like there is this year, and that's relatively cool. But on average, if you take those kind of fluctuations into account, you see that the temperature is going up and up. But you also see that the temperature is not going up everywhere at the same rate. In particular, you see that the North Pole is getting warmer and much faster at pretty much double the rate than anything else in the world. And this is because of these kind of feedback effects. Because if it gets warmer, the polar ice caps will melt. So locally there is less reflection of sunlight. So there's going to be more sunlight coming in to warm up the water. If the water gets warmer of the ocean, then there will be more ice to melt, so less albedo, etc., etc. Same stories can be told with clouds. If for some whatever reason you would have more clouds or higher clouds, you would have more reflection, you would have a higher albedo, and then you would get a lower temperature. So clouds in that sense can be a bit of a balancing act in the climate system. Of course, there's also the ocean. Now we think of the ocean in climate change as one thing, and I'll address that in one slide later. But there's also the acidity, because CO2, if we add that to the ocean, becomes an acid, becomes carbon acid. And sure enough, the acidity of the ocean has gone down. The pH value of the ocean, the acidity has gone up. The pH value of the ocean has gone down. So from 8.2 to something closer to 8. Depending on the scenario that we're looking at, the pH would go down quite a lot more, which is something that's fairly hard to adapt for biological species in the ocean. Now for sea level rise, we see that the total amount of sea level rise over the past century or so has been roughly, let's see, that's this thick black line going from, so in 1900 the average sea level was roughly 170 millimeters, so 16 centimeters or 17 centimeters, so that's, 4, 5, 6, 7 inches lower than it's at this day. Why is that? The typical answer for why do we have sea level rise is not per se the only one, is not the sole contributor, but that's the brown line over here. So glaciers and ice sheets, sure, on Greenland, on Antarctica, are melting. If they're melting, or at least on Greenland, Antarctica is only now starting to melt seriously as well. If they're melting, then all that water has to go somewhere. It goes into the ocean. So the ocean has to rise. As it turns out, another much more consistent increase is the orange line over here. And that is the very simple fact that the ocean is getting warmer. If the ocean is getting warmer, then warm water has a lower density, so it expands. So it gets bigger. It can't go to the side because there's already continents, so the only place it can go is up. If it goes up, then we get expansion and then we get sea level rise. Funnily enough, this has been compensated for some bit, and especially in the 60s and such, this has been compensated by terrestrial water storage. What do we mean by that? Well, water just being stored, what it is, right? Water just being stored on land. That could be in the ground. Actually, there's not that much groundwater change, not all that much. But what happened in the 50s and 60s? A lot. Dam building. The Three Gorges Dam, the Hoover Dam was a little bit earlier. The Aswan Dam in Egypt, etc., etc. All those kind of massive dam building projects stored an enormous amount of water. There was actually a measurable amount of water in terms of sea level rise. So I guess the mitigation point there is let's keep on building dams and let's just store as much water as possible on land. I'm not sure that this is super feasible. Okay, now finally, let's have a look at what hurricanes. There is not a lot of evidence that on average the amount of hurricanes are gonna get more frequent or anything like that. Maybe over the Atlantic. We see a lot of red over here, the number of hurricanes per year. But if you look over Asia, and there are way more, or in the Indian Ocean, and there are way more hurricanes in the Indian Ocean than there are in the Atlantic, you see actually that the number might decrease. What is likely to increase, on the other hand, is the amount of the strength of the absolutely strongest hurricanes. And in some sense, you can imagine that the hurricanes are fueled by warm water. If the water is getting warmer, then there is more potential for more vigorous hurricanes, for more vigorous turbulence, basically. And that's what a hurricane in the end is. It's one big eddy swirling around its axis and basically feeding on this very warm and very energetic ocean water. So the warmer the water, the stronger the hurricanes, the stronger the strongest hurricanes will be. And we see a projection that that would increase by significant amounts over the next couple of decades. Okay, forest fires. Of course, for forest fires, most forest fires in the US are ignited by some kind of human intervention, by some kind of arson. That is not in itself, that does not become more extreme by climate change. What does become more extreme by climate change, of course, is the susceptibility for fires, and if so, they'll become bigger, simply because fires become, because the climate is warmer. There's a larger area in the US and in the world that is susceptible, that's warm enough to get a massive fire, and larger part of the globe, but also the amount of area that one single fire can cover will be bigger in a drier and warmer environment. So if we look at the top 20 largest California wildfires, and this is data from mid-September, so it may have been slightly worse from now, but from the top 20, 3, 4, 5, 6 are actually from this year. And if you look at the other numbers, many of them are pretty recent as well. This is a general theme of general joke, I guess, in climate science, that we shouldn't think about this year as one of the warmest years in history so far. We should think about it as one of the coolest years for the next 100 years. So, what can we do? And we only have a few minutes left to talk about that. Well, one is get used to it. I guess we'll need to do some of that. One is massive reduction. And one is see if we can fix the system a bit. See if we can create climate change in the right direction. That's what we call geoengineering. Geoengineering is a very scary thought, but we might as well, as sensible people, think about it before somebody is going to do it in a reckless manner. And then finally, for geoengineering, so we should get used to it. We should adaptation. We should reduce as much as we can. But one thing that people tend to talk less about, because probably it's dangerous, probably it's poorly understood, but we could start to try and capture CO2 straight out of the air and store it, which works, but to capture all the CO2 that we're producing each year, you would need roughly the 1/3 of the amount of energy that we're using on the globe each year. People have talked about putting small mirrors in space everywhere so that some of the sunlight is being reflected. Some afforestation, which happens already, of course, replanting forests somewhere, but there is limited space for us to do so. You could do something very similar in the ocean, as in you could put algae, make sure that there are more algae in the ocean, and algae are green and retrieve CO2 from the ocean and therefore in the end from the atmosphere. Another option would be to do cloud seeding, and cloud seeding is essentially adding small aerosols, keep on adding aerosols to the atmosphere, and those aerosols there would be cloud droplets forming on those aerosols, and therefore those clouds would hang in the air and there would be light reflecting from those clouds. All these kind of concepts have several disadvantages. One would be that they're only attacking the source. So the moment you stop doing your cloud seeding, your temperature goes back to where it was. Another fairly obvious one, if you're creating clouds in one place, you have no clue how that's going to affect the air in another place. So creating clouds in, let's say, Arizona and making it rain in Arizona might very well make it yet drier in New Mexico, which would obviously create political issues, and even worse if that's between countries. So in all, human-induced climate change is real. Global temperature goes up. Locally and for a very short time, it may be very differently. But all in all, the global temperature, even if it doesn't feel like that on a day like today, where I'm wearing a sweater because it's starting to get fall, global temperature goes up. Don't mix up weather with climate. Geoengineering might help delay global warming, but there could be very unintended consequences, so we need to think about it very well. This is getting a very short-ish term issue. To keep things reasonable, to keep things within 2 or 3 degrees of warming, without some very drastic consequences, some very drastic measures in the slightly later future, we really need to act now. However, there is no such thing as a one big threshold that we cannot get over, and if we're over, it's completely doomed, and if we're below, it's everything fine. Basically, everything we can do as a society, the more we can do, the better. And the less we do, the worse. All right, I've got my email address here in case you want to contact me. Some of the material that I showed you today are from the Carbon Brief website that I find helpful in some of their explanations. Skeptical Science has some decent rebuttals of popular anti-climate science arguments. And of course, there's always the IPCC reports. The 5th assessment report, based on every climate model, climate scientist in the world, is already a number of years old, and the first results of the 6th model are coming in from next year on. Okay, and with that, thank you so much for listening. Bye.